It is my distinct honor and pleasure to introduce my mentor for my doctoral degree. I went to Cal, so I'm very familiar with the Berkeley way of things. It's very interesting for George to put these pictures up. This is him at a younger age. On your left, running the mile at Queens College, which is where he got his undergraduate degree. Mile relay, excuse me. Mile relay. And this is him also. One of the things you'll hear about today are a number of the studies that Dr. Brooks has been the primary investigator on and also participant. One of the things he taught us, and I'm sure Dr. Bagley and myself and Dr. Lee all agree with, when you go to do any kind of experiments in the lab, just like in your ex-phys lab, you get to be a subject. And in this situation, there are a number of different catheters going in and out of his leg and arm, taking samples of this, infusing that, and to get the first set of data on whatever he was studying. Dr. Brooks got his degree, as I said, Queens College in New York native. But I found out today at lunch, it's 1971 when he came to the Berkeley campus as a temporary position for a year to see if he was going to take over the exercise physiology position. He was offered that job and has been there now for 46 years. I first met him in '75 when I was a freshman at Cal, and he gave a guest lecture. And I thought it was very interesting stuff, but it wasn't until my senior year when I took ex-phys that I literally got hooked in the exercise physiology world and didn't leave the PE building, the gym at that time, Harmon Gymnasium, after that. It is my distinct honor to have a friend, colleague, mentor, Dr. George Brooks.
Well, hi, everybody. I show this picture to my class, and they have no clue who it is. Then I have to tell them, your professors were 18 also. So I'm happy to be here today, actually happy to be anywhere. And so we were a little late coming for lunch. So from the boards and the Cinders, from the track, basically, to the Neuro ICU, where the things we learned about exercise apply to the brain after injury. So by way of disclosure, we had support from different agencies, and we had support from industry, and we have support from my company. Okay, additional disclosures. At various times, all the things to be presented today were characterized as wrong, impossible, nonsense, rubbish, So we are actually in clinical trials using lessons from exercise physiology to rescue people in the brain. So lactate 50 years ago was a metabolic waste product, a fatigue agent, a poison. Now lactate is understanding has changed. It's a fuel source, it's a gluconeogenic precursor, and a signaling molecule, a lactohormone. You guys see the red eye? Okay. So, history of interest. Well, yeah, I wanted to run. And I got pretty good, but not as good as I wanted to get. So I said to my coach, why can't I make the Olympic team? And he said, you have too much lactic acid, you have an oxygen debt. I said, first I had original sin. Now I have lactic acidosis. I hate lactic acid. What is it? Why do I have too much? So, Coach Patty said, go read about it. So I read about this guy, Otto Meyerhoff. He had half a frog in a jar. There are no lungs, there's no circulation, there's no oxygen. The electrical wires here made the muscles contract. After a while, the muscles built up a lot of lactic acid and fatigue. So there was no perfusion, there was no oxygen, but he got the Nobel Prize. So I guess no hope for me. But at the same time, he was a very, very smart man. He said, God both of them. I mean, God doesn't play dice with humans. So if there's something in nature, why is it there? Is it there to make you cramp up and die? Is it? Didn't make any sense. So actually, I've been studying it. So Einstein was a contemporary of the same ideas in physiology. So Marialice did get the Nobel Prize. And also about the same time, his professor, actually the professor got the Nobel Prize after he was on Harvard, and he studied cells and culture. He studied cancer cells and culture. And if you understand German, this means a little bit of oxygen, this means a lot of oxygen. These cells always glycolized, that was made lactate, lactic acid, regardless of the presence of oxygen. So that was actually a clue that cells can glycolize fast even when there's a lot of oxygen. And subsequently, jumping decades ahead, the Corys studied gluconeogenesis, and their idea was this, that in the liver, glucose can break down and make lactate. That's true. Glucose could go around the body and go to the muscle and be made into lactate, and in the circulation could bring it back to the liver. So this was the so-called Cory stuff. Actually, they actually never measured it in person, but this was done on cadence. They got a Nobel Prize in 1947. So generally held ideas. Glycogen is a precursor for lactate. That's known. That's true. Marialice discovered that. Glycogen breakdown, lactic acid increases under anaerobic conditions. That's true. If you don't have any oxygen, that's all you can do. And then lactic acid causes fatigue. So here's the idea of the different concept. We call this the lactate shuttle. Is that there's utility in making lactate. So here we know now that a fast glycolytic or white fiber, when it contracts, it breaks down and makes lactate. And then lactate can go into the blood or around the body, reach the heart, but also reperfuse the adjacent fibers, which are red and oxidative. So some of the lactate can go to an adjacent fiber, enter the mitochondria, and be burned as a fuel, as well as some of the lactate leaving will reperfuse the muscle within seconds, and they're during exercise and become a fuel. So the idea is that the body can make this sort of currency of energy substrate called lactate, and it can use it in an adjacent fiber, a different part of the body. That was the original idea. At that time, we didn't think about studying the brain, or I'll tell you about that. We didn't think about studying the heart, and we didn't think about studying the liver. So, here's a photograph of what our apparatus looked like at the time. And some of my wife's friends says, "Who's this?" You have brown hair? Here's the metabolism chamber. Here's the rat. We got very good at putting catheters or tubes in the jugular and the carotid artery. And just like you do in the lab, we can measure oxygen consumption. This is a handheld treadmill. We can infuse tracer, let the expired air, and take blood samples. This is Dr. Casey Donovan, who's now at the University of Southern California. And also, the same apparatus that Dr. Kern used for her dissertation. So we can study rats, trained and untrained, to rest and exercise, and then with different substrates, amino acids, glucose, and lactate. So here's from the lactate studies. And I think you know, everybody knows that if you're trained and you exercise, your lactate is lower. And the original idea was, well, you have more oxygen, so you have less anaerobic production of lactate. So we had rats that were trained and untrained. We studied them at rest. And lactate production is prominent at rest. So right now we're producing lactate. And we're fully aerobic. And during easy exercise, the blood lactate will rise. And in hard exercise, the lactate will rise. But in the untrained animals, the lactate will go really high, get up to, in this case, 5 millimolar. And in the trained animals, the lactate level will go to only about 2 millimolar. But you can see the production is the same. So, even during exercise, if you're trained to producing lactate, but you're clearing it, you're using it, you're burning it, and you're making it into glucose. So the big thing that happens with training is that you produce that lactate, but you clear it. So at that time, we had this subject who volunteered for his own experiment, and this was the first tracer experiment on a human, where we used not radioactive lactate, but carbon-13, which is stable. We measured in mass spectrometry. So over Christmas, about 1985, the thing to do was to inject some lactate into an artery, take blood samples, collect expired air, measure the turnover and oxidation of lactate. Here are the data. Also, by the way, I have other pictures. This is Dr. Tom Weber, MD, PhD on our campus. This is the dissertation of Dr. Azio, who's now at the University of Colorado. So there's always lactate production at rest. Easy exercise, lactate production goes up. This is 50% max, and this is 75% max. You can see lactate production goes up. Collecting expired air, you can find out about half of it is removed as CO2 is burned at rest, and then about 80% and 75% in exercise. So lactate production is continuous, and most of it's used by the mitochondrial oxidants. And disposable is most of it is oxidants during exercise, whether it's easy or hard. So a couple of lessons to take away. Lactate production is continuous. We know now if you have carbohydrate and you're just at resting, you make more lactate than if you don't have dietary carbohydrate. And lactate production is high during sustained exercise, but it's removed mostly by oxidation. So that was happening. I was not using enough. So who knew? Now, to find out where in the body this happens, we had to do some invasive work. And this was done at San Francisco VA, or at UCSF cardiology. So we took our bicycle odometer, we put it over a cardiac catheterization table. We put a number of catheters or tubes in. So we had a number of different sampling sites. So from your anatomy, you know that the venous return from your arm goes up the shoulder, goes to your superior vena cava, goes to your right atrium. So we could put a catheter up the arm, put it into the right atrium, twist it around and find the coronary sinus, which is the venous drainage from the heart. And also, you know that we can put a catheter up the arm, down through the right atrium, down the inferior vena cava into the liver, and also one that goes up all the way down into the leg, so we can measure lactate metabolism. And also one catheter just sort of in the middle of the biceps, so we can sample an inactive muscle, we can sample from the working muscles, we can sample from the liver and the heart. So what do we find out? Well, actually, there were some data on this for rest previously. So for a resting person, fatty acids are most of the fuel for the heart at rest. But there's some glucose that's obligatory. And lactate is low at rest, but it's still 13% of the fuel used by the heart. And then during this easy exercise, 40% of VO2 max, the lactate level rises. And now lactate is more than half the fuel for the heart. Glucose is still about 4%, but the contribution of lipids is decreasing. This is an example of lactate shuttling. The muscles are making lactate, releasing it into the circulation. It's being taken up and fueling the heart. So indeed, as a general principle, when some tissue is releasing lactate, it's going to circulate around and be used other places. So during exercise, blood lactate from working muscles fuels the heart. This is aerobic glycolysis. New. Now, what about the effects of training on these processes? If you're trained, do you do this more or less? The shuttle actually, I'm showing you the shuttle more. And you can produce more and remove more. So we use a combination of isotope tracers. We use carbon-labeled lactate, and deuterated glucose, and muscle biopsies. We measured exchange across the limb during rest and exercise before and after training. So here's a movie. This young man actually has lung catheters in his femoral artery and femoral vein. And we're taking blood samples simultaneously while he's exercising. This happens to be after training, but we did it before training, and we did it at rest, and we did it several levels of exercise. This is Dr. Ann Freeland, who is now faculty at Stanford, Dr. G. Mopel. At the time, he was head of cardiology at University of Colorado. Okay, so we can measure this stuff. And we use the trick in isotope tracer physiology. When we give 13C lactate, the carbon is heavy by mass plus 1, because carbon is 12, so this is 13. And we also use glucose. And we can measure the incorporation of lactate into glucose, and that'll tell us the arterial, that will tell us the rate of gluconeogenesis. And also systemic, also we can measure the production and removal of lactate and glucose. So here's sort of the punchline of this about the Cori cycle, which the Coris never measured, but which we did. And we have people at rest before and after training. This is glucose production from our lactate at rest. You can see lactate training really increases your ability to do gluconeogenesis. And then before training, these are the lighter bars. This is 25% of VO2 max before training. You see gluconeogenesis goes up, very easy exercise. But during hard exercise, probably because the perfusion of the liver is reduced at 65% of max before training, gluconeogenesis goes down. After people are trained, gluconeogenesis goes up in same power output as this response before training. The training effect is here. This is 65% of the new VO2 max, which is now about a third more power. So 20 to 25% of the disposable lactate is to glucose, which then actually gets burned. So the rest of it, 80 to 75 or 80% of lactate disposal is by oxidation. So training improves the ability to maintain glycemia, blood glucose control, by improving the capacity for gluconeogenesis. So we have here the pictures of the Coris, Dr. Brian Bergman, now at the University of Colorado, in Denver, specific to Dr. Now, one of the things we noticed is that the exchange of lactate across the leg and the uptake of lactate and its oxidation followed a curvilinear response. So this is before training, and this is after training. What you can see is that the ability to remove lactate is somewhat concentration dependent, but it follows this curvilinear relationship. So biochemists would say it's like there's a saturation. Because as you increase the concentration, you get more lactate, but it's going to level up. So there's aerobic glycolysis, working muscles simultaneously producing and removing lactate. Nobody can see that without putting a tracer in. So who knew that there's simultaneous production and removal of lactate? And for somebody who's trained, training allows you to keep it balanced. So you can exercise harder, you can produce more lactate, you can burn more lactate, make more glucose, which you burn. And you really have an augmented fuel. brains and muscles, this time rats, and studied the uptake of lactate by these vesicles. And we found that there was stereospecificity, there were concentration effects, there were pH effects, there was bidirectionality, and the uptake and exchange was could be inhibited by specific metabolites. So here are the data. This is Dr. David Roth with his wife Catherine. They met in my class. So there's more going on here than meets the eye. So this shows the stereospecificity. So if we take these vesicles, and David took these vesicles, and he incubated them with lactate, and he increased the lactate concentration. You see the uptake here goes up fast, and it bends over, reaches saturation point. And this is the D isomer. So this probably doesn't share the transporter, does not share the transporter. But this is simple diffusion, and this is a facilitated exchange. The exchanges are KS and GPX. So we now know that there are lactate transporters. These lactate transporters facilitate the exchange of lactate across the cell membranes. And when you train, you get more transporters, so you can remove lactate better. The lactate transport proteins are called monocarboxylate transporters. The first one discovered was called MCT1. That exists in the red muscle in the heart. Subsequently, another isoform was found, and that was identified as MCT2. So this is work in our lab by Takeshi Hashimoto, Elijah Hussein, and my colleague Daniel Alcalpa was on Berkeley faculty. And we're looking for expression of monocarboxylate transporters in muscle, and I actually skipped that slide. I don't have that here, but we look to see if there were other tissues. And these are brain tissues. So this is neuron hippocampus, and the isoform expressed there is MCT2. It also co-localizes with the cytochrome oxidase, so this transporters are mainly in the mitochondria. This is a neuronal marker, and this is where we have the co-localization, the color So the lactate transporters are ubiquitous. With training, they go way up. They exist in other tissues too. And one day, some years ago, these two guys show up. They're UCLA guys, Westwood guys. Aren't they nicely dressed? So this is Dr. Neil Martin, who was chief of surgery at the time, chief scientist. And they came to us with this problem. Traumatic brain injury is far too common. The CDC estimates that the occurrence of traumatic brain injury will be almost 2 million cases a year, in which hundreds of thousands of people require hospitalization. And there are far more sports-related injuries as well. In Los Angeles, where the colleagues take care of these patients, it's about one person a day is in a car wreck or has some other kind of problem. They're in the Neuro ICU and clinging for life. So what did they find? There's a lot of, every injury is different, so there's a lot of scattering of data, and people are all different. And but what they showed here is that if you really get the brain to take up lactate, because they put catheters in, to show you sort of the setup. The patients who survived and did better, their brains were taking up lactate. And so Dr. Martin and Glenn got the idea, well, lactate could be a brain fuel. And if you're injured, it was known that the ability of the brain to use glucose, sugar, is depressed. So the idea was that, well, maybe this alternative fuel would the brain, and maybe that's why these guys did this. And doing better means that they lived, or they came out of the whole situation with an IQ close to where they started. So we did these experiments. So anyhow, Dr. Martin's submitted a grant to the NIH, and they said, the reviewer said, I don't know biochemistry, because lactate's bad. And furthermore, you're not a careful investigator, because to measure what goes into the brain, you have to put a catheter in the jugular bulb, put it up into the brain, measure what goes into the artery, and then you need to measure brain blood flow. They said, you don't know biochemistry, you're not careful. What do we do? I said, that's what they always say, don't worry about it. So do a couple patients, we get a small grant, we get a big grant, it's called the program project, and studies. So this is what it looks like. This person, sorry, this is not the, I didn't have to try and we can measure the, we can put an isotope in, we can take arterial samples, we can take venous samples, we can measure what happens across the brain. And this is to measure brain blood flow. Now, people were volunteering daily to be in the study. But the hang-up was, if you get control data, who's going to volunteer for this? And the ethical review board was quite severe. It took quite a long time to approve. Doing this to somebody who didn't have a brain. Anyhow, so some of the data. So this is published in clinical journals. This is Mike Horning, this is our spectrometrist, this is a colleague of ours. This is the rate of gluconeogenesis, as I described before. We can measure gluconeogenesis by the incorporation of carbon-13 from lactate into glucose. And you can see that people after injury, the rate of gluconeogenesis is way higher than in control studies. So what the body's doing after injury is rallying its carbohydrate resources. It's breaking down glycogen to make lactate, which goes to the liver and makes glucose. So the glucose being produced from lactate. So lactate is fueling the brain after injury. And also one of the things we were concerned about is that after injury, the ability of the brain to take up glucose is suppressed. That was what I'm not going to show you that. But we have here the uptake of lactate by the brain after injury compared to control. And you can see the uptake is significant. So the injured brain, well, it can't take up glucose very well. It can take up to use lactate. Just like a muscle. So here are the data on the controls and the traumatic brain injury subjects. Glucose is a major fuel for the brain, but in people who are close to Dr. Bessie, 68% of that glucose comes from lactate. Lactate itself is taken up by the brain, close to 10% of the fuel. For people after injury, who can't take up glucose uptake is really very suppressed. Most of it comes from gluconeogenesis of lactate, and the lactate is taken up by the brain directly. So in these cases, there deoxyglucose. This is a picture of somebody who's got an injury. They were given this tracer, which shows you glucose uptake, not lactate uptake. We'll talk about lactate indirectly here. So here's a lesion. And the red spot here is glucose metabolism is high. There's a lesion here. They did that on one day. And then on the next day, they gave him deoxyglucose again, but instead gave lactate. And you can see lactate actually is the preferred fuel that actually suppresses the glucose uptake. So this is the goal. If you live to take a glucose alternative, work around it by giving an alternative fuel. Okay, so this brings us to where we are right now. We're trying to develop a system to treat these people. The system will look like this. There has to be a sensor to measure levels of glucose and lactate in the blood or brain. There has to be a controller. There has to be a controller that controls us to deliver lactate, glucose, and other medicines to the person. And then be able to measure this in real time and make this closed loop system. Yeah, some of you know about the artificial pancreas, which is conversion. So we went to this company called AAA, and we said we need to make a prototype. It cost $2 million. So I just really good with things. So we got a glucose analyzer, a lactate analyzer, a thing called a Raspberry Pi, and hooked it up to a microprocessor. So we have a working prototype. Total cost, smart batteries, not batteries, and here, $400. Quite a saving. Now we're trying to package this, and it kind of looks kind of funky, but my saver is Sam Vicente. Sam Vicente is famous in industrial design because he designed the iPad, the IBM ThinkPad, and he designed most of the HTTP printers. So he worked for AT, he worked for IBM, now he has his own company, and he's designing our parts. More expensive. God hope is one. We'll work for food and drink. Okay, but one of the things we're trying to work on also is lactate therapy. There's a whole story there, which is not explored in these cases. But lactate when lactate is high in diabetes, chance of probability of getting type 2 diabetes. So, the discovery of Lactate Shuttle. This is sort of our punchline here. If it is glycolytic metabolism, lactate will be the body. If there is oxidative metabolism, lactate will be the substrate. So what's neat about this can happen within a cell, with glycolysis, with lactate, the lactate be taken up by the mitochondria and oxidized. Or it can be legs working and produce lactate in the heart, the vehicle is lactate. Or it can be a muscle that is contracting, making lactate, which is going on in the liver for gluconeogenesis, and the vehicle is done. Or it could be that tissues around the body will make lactate in the brain, and lactate is the vehicle. In the case of traumatic brain injury, it might be the rescue. So this a couple years ago, this is what we look like in person. I like to brag about my group, say we're genetically superior, because we have everybody's genes. So, thanks a lot. Thank you for your attention.
Thank you, Dr. Brooks. Anybody have any questions? Open it up for some questions.
So the lactate shuttle is referring those transporters in the mitochondria or the whole system?
Good question. Where are the transporters? They're in the plasma membrane. It's also in the mitochondria.
Okay, so
Yeah. So lactate is like any metabolite. It goes from high concentration to low. The one next to concentration below is looking up and burning. So that you need to get across those membrane barriers. And there is those concentration. There's Transporters. There's no Transporters are move a lactate anion in the counter. Usually sodium, but in the gut, usually a proton, and the gut is sodium. So we make Cytomax sodium.
thank you very much.
Yeah.
And I'm wondering about these marathoners that are habitually victorious. Is there a genetic predisposition to metabolize lactate acid more efficiently than the rest of it?
Yeah, to get right into the question, what about the marathon runners who were successful most of the time? So we did an experiment some years ago. We had an Australian classmate of Marialice's, and he was a 145 and 800 meter guy. He didn't have training, so we went and asked the question, what does a marathon runner earn? The idea is, well, they have to burn fat because they don't have enough glycogen. But self-selected pace, people are running at an RER of about 0.95. So what does that mean? That means they're using carbohydrate. But there's not enough glycogen in our muscles. For the last 2 hours and some minutes now. So what the body has to do is mobilize all its glycogen. So lactate around the body. The question is there a genetic predisposition to running fast? I think there is. Fast and long.
Thanks for a very informative talk. My question is, well, you mentioned that that lactic acid has gotten a bad rap in the past for causing muscle fatigue, soreness, etc. Now that it's kind of like off the hook, so to speak, tell me, what does cause muscle fatigue and soreness?
Yeah, so that was a great question. I heard it. And so this is controversial. If you look at the glycolytic pathway and you add up all the carbon and hydrogen atoms and oxygen atoms, you come down to pyruvate. Then the next step, catalyzed by lactate dehydrogenase, takes pyruvate plus a proton plus NADH and makes lactate. So the last step of glycolysis actually is an alkalizing step. That makes the question even more profound because, okay, when we have lactate, it usually comes with acid acidosis. So what's the source of the proton? Well, people have written about it. It could be from ATP hydrolysis. It could be from CO2. Other processes give rise to protein. So the lactate anion basically is the benign part, but it's historically been associated with lactic acidosis. This has been a big problem in the clinical world, understanding this, but in the clinical world, not just sports medicine and exercise physiology, but patients in the ICU. So what gives rise to the proton and how do you manage the proton? That's a classic issue. One way to lower the proton concentration is actually to give lactate. The body will remove lactate and proton because transporters are supporters. So yeah, so where does this acidosis come from? That's your question, and that's controversial. Glycolysis makes lactate. Yeah.
Physiologically or chemically, why does a brain that experienced a traumatic injury uptake lactate more readily than glucose?
Yeah, so the question is, what limits the glucose uptake? Because for 45 years I taught that the brain uses glucose almost exclusively. But now there's another part of the lactate shuttle called the astrocyte neuron lactate shuttle. So astrocytes, which are most of the cells, currently take up glucose, and neurons run on lactate. That's the normal sequence. But your question is, what happens to those astrocytes globally in the brain, which makes them shut down? Well, there are these neural networks. I read about them and I've seen images, but there really is a neural network. So after an injury, the brain shuts down. It's not the part that's injured, but glucose uptake regionally. In other regions is suppressed also. So we don't know why everything shuts down, but we know that the cerebral uptake of glucose is limited after injury. So it's just a maneuver now is to bypass that blockage. Why is the brain taking up glucose? My hypothesis is that there's a redox change at FDH. Because it tends to just, you might say, well, the brain prefers glucose, we just diffuse glucose. If it doesn't get in, glycolysis is so the maneuver is to bypass that. And I think it's a redox change which occurs as part of the study. And again, it was really incredible because in the TBI field they have there's two injuries. There's a coup and counter coup. If you get whacked on this side of the head, you might get a laceration. But your brain is going to accelerate inside your skull and you'll have a bruise on this side. So there are always at least two injuries, coup and counter coup. And depending on how you get bumped or whatever, your frontal to rear, you have different kinds of injuries. But the brain goes to sleep. The astrocytes there. We'll deal with the microphone. Dr. Bagley will decide.
So I don't know if I saw the last slide correctly, but is a greater concentration of plasma lactate associated with greater incidence of type 2 diabetes? Did I see that correctly? And how's that?
I'm trying to get money to understand this. All my grant applications, at least 10 have been rejected. People don't want to look at that. But here's the probability that somebody who's not diabetic is pre-diabetic, and as their blood lactate rises, the chance of converting to type 2 diabetes goes up. Okay, so I could have brought a model to try to explain that. It has to do with insulin action and glucose tolerance.
It's a really big block, so they can't take glucose or lactate.
Yeah, the lactate becomes a preferential fuel. And it does get used. So the question I put up here is lactate is buildup of lactate in diabetes a problem, or is it a way to rescue? Is it an alternative carbohydrate the body's making?
Trying to figure that out.
We would love to try.
So, is the mechanism for lactate being transported into the mitochondria through the MCT2? Does it go through lactate dehydrogenase and then produce pyruvate, and then it can go through the Krebs cycle again?
I didn't show this. This is my answer slide. So this is the answer to the question. So where does lactate get in? So we published on this, and we use different kinds of techniques to fractionate cells. We use immunoprecipitation to show this. So this is mitochondria. This is the outer membrane. This is the inner membrane. This is glycolysis. Nitrogen to pyruvate, LDH. The question was about LDH. Where is LDH? LDH makes lactate. So we know that right now our lactate pyruvate ratio is about 10. So we have 10 times more lactate than pyruvate. People who wrote the textbooks just ignored this. And then we measured the venous effluent from working muscle. And the lactate pyruvate ratio is about 650, sometimes 700. So glycolysis makes lactate. It doesn't stop it by removing this notion of something. It can't happen. Because this LDH equals constant 1,000. So, but then how do you get back? The question is really, how do you get back to pyruvate? Okay, so on your mitochondrial membrane, you have found what we call lactate oxidation complex. There's MCT1 in muscle and in heart. And it's found cytochrome oxidase and lactate dehydrogenase. So the idea is that this gives us pyruvate. Pyruvate is for you, old-time chemists, sorry. Yes, so there are different isomers in MCTs. MCT1 is mostly muscle part. MCT2 is the brain. MCT3 is the retina. And MCT4 is in the white skeletons. It's part of a large gene family called SLC. And there are other transporters in there that transport other things, including amino acids. First four are pyruvate exchangers. Also, ketones can come in. We talked over lunch today about ketonic diet. Ketones come by Okay, so are there any old-time chemists in here like me? Assay lactate. If you look at the handbook of biochemistry by Berkeley, and this book that we will use. How do you assay lactate? Using lactate hydrogenase, knowing that the equilibrium will always take pyruvate in the lactate. So if you have lactate, how do you get this immediate reaction to go backwards? And just you can see there's redox change in the spectrum. How do you go backwards? Well, in the assay, what you do is you have a hydrogen there. Pyruvate and hydrogen and use the pyruvate. So the way this enzyme can be used to lactate by converting pyruvate by removing pyruvate. So that was my idea about how this thing might work. But the mitochondria do is they remove the pyruvate. And anybody who tries to measure pyruvate in the mitochondria finds that it's very low. That's how the system works. The answer to the question is lactate gets in. There's LDH in the mitochondria that makes pyruvate, and the pyruvate gets removed, and that causes this concentration gradient that allows it to live. Yes?
Dr. Brooks, I think I saw you flash a slide that talked about the original idea that when we became anaerobic, we produced more lactate. And of course now I think we've moved past that idea. So have the views of lactate and role of metabolism kind of mirrored the notions of aerobic versus anaerobic metabolism?
Not completely. So I use the word glycolytic. I use glycolytic and oxygen. And then things sort of jive. But in sports medicine, exercise, physiology, traditionally we talk about powerlifting, muscle power, sprinting, that kind of thing, being anaerobic. But the idea was that the lactate is made because there's not enough oxygen. But there's enough oxygen. And then Barbara showed that the cancer cells. We show that on people resting. We're making lactate all the time, sitting there. After carbohydrate, lactate production goes up. So it's aerobic lactate production. So we try to, get this idea out of people's mind that when you see lactate, it didn't mean that there was not enough oxygen. So in the clinic, somebody comes in, lactate's elevated. Traditionally, they would give oxygen. But oxygen, they weren't making lactate because of lack of oxygen. Or they would say, oh, we're going to buffer this, give bicarbonate. And people could convulse. It's not good. So there recently has been a paper in The Lancet that I can share. And it was written by a man named Ronaldo Bellomo. It's an Italian name. He's not a soccer player. And he's now works in Australia. He's written an article in The Lancet, a big medical journal. He actually uses my diagrams. And I use his diagrams because they were drawn by the artist who works for The Lancet. Better than mine. he's talked about how this knowledge can be used in clinical medicine. I talked about rescuing people that have traumatic brain injury. It's given sometimes to kids with dengue fever. It's given to people with pancreatitis and hepatitis. So there are all these clinical experiments going on all around the world using lactate as a treatment in the clinic. Who has that? That's why we need to do these clinical trials, so it's efficacious, not injurious, and beneficial. And then we'll have to, do clinical trials in every kind of situation where we need to demonstrate. So TBI would be different, pancreatitis, hepatitis, dengue fever. But there are experiments out there in literature showing there's efficacy in all these cases. Now, one thing I didn't mention is that when we give sodium lactate, the lactate gets removed with a proton. So it turns out that giving lactate in any form is a powerful buffer because it will force the removal of the proton that's there. So when you give it, it actually optimizes. The sodium is really interesting for treating brain injury. After people are bombed, the brain swells, so inflammation is common. So sometimes doctors will give sodium chloride, and hypotonic sodium chloride. And that's also used after severe hydration and hyponatremia. So people, so clinicians will give sodium chloride. But the advantage of giving lactate over sodium chloride is that there's a receptor for lactate. It's called PR81, glycoprotein 81. It's the lactate receptor, and it's in the sibling cascade of inflammation that's really at the top. So giving lactate will prevent brain swelling. Giving sodium lactate is probably maybe more ideal.
So with the increase of, or the increased use of lactate out by the brain after a traumatic brain injury could potentially, like submaximal exercise be used as a type of therapy for like maybe mild traumatic brain injuries, just the availability of lactate in the system?
That's a great question. So I think everybody heard it, right? So in the progression, as I understand it, for return to play after concussion, is your headache's relieved, and you can work out and not get a headache. And then work out, and then you do contact, and not get a headache. Return to play. So working out, I think, is the key thing, right? So why not use a lactate supplement to help get people over the concussion? So we have a grant pending. Yeah, so I think that's a great idea. So this is what we call translational medicine, taking basic science and applying it to something which results in concussion. So my wife's a sports medicine doctor. She's an expert in this field. And give us something, we can help these people.
You also mentioned ketones as an alternative fuel source for brain. Was there any increase in the use of ketones as a source after brain?
Yes, that's another great question. So in the Neuro ICU, there's this problem is nourishing the patients. So you saw gluconeogenesis was way up. The patients are not being fed up. So after our studies are, by the time the person is injured, gets stabilized, and they get permission with their legal representatives to do the study, it's sometimes 5 days. At that time, their glycogen is gone. And the doctors are really afraid to feed them. Because if they get diarrhea in the bed, it's bad. Or if they throw up, it's worse, because they might aspirate. So they tend to starve patients. So, but some of our colleagues also found that if you get so many ketotic glycosate and the ketones share the MCTs. So but in 1990, David Roth, now I showed that transporters prefer lactate over hydrolate, over alanine, over ketones. But ketones can get in. So in somebody who's starving, the body is very to really get to supply energy to the brain, right? So the transporters go up. In a rat study, one of the colleges at UCLA are our antibodies to MCTs. They found that the animal model is 100% increase in expression of protein after 24 hours. So the brain is really constructed to try to minimize this energy deficit. And it can't take lactate. But if you're 5 days out, the lactate is going to be low. But ketones can be right. There's another alternative.
Just to follow up on this question.
How do ketones cross the blood-brain barrier to be accessed as a fuel source?
Okay. So, we don't have plasma membrane. This is just a mitochondria. If you imagine that this is a plasma membrane, this is the evidence so the ketones rise in the blood, and then they can permeate the membrane. So maybe we need to have a version of this where you use a mitochondrial out of membrane, mitochondrial membrane, that we can stick in the other transporter isomers. So again, MCT1 is in muscle and heart. MCT4, red muscle. MCT4 is in white muscle. MCT2 is in the brain. It's in cancer cells. And MCT3 is red blood.
Thanks, Dr. Brooks.